I am Ivan Robin from Leti. I'm here today because I'm replacing Alexandre Lagrange, who couldn't make it today. And I'm going to talk today. I'm going to try to give you an overview about the market of solid-state lighting LEDs, mainly based on gallium nitride. And I'm going to try to show how nanophotonics is involved in the industrial world with those LED technologies. So well, the lighting consumption is very big. So we can just think about this number because 200 nuclear reactors are used just to light the world. So the main thing with LEDs is to try to reduce the electrical consumption linked to lighting. Just to go quick on this. So because there are so many LEDs, it's a huge market. And what is predicted now is that it's going to keep rising until 2018, and it's going to reach a top, and then it should decrease because of this is what is predicted now. Well, it should decrease because of the lifetime of the LEDs that is very long. So we're not going to have to replace them as much as before, and as we can see is that the general lighting is going to eat the most part of the market. We think it's going to decrease, but so maybe the thing that is going to make us change our LEDs is to bring more than light with an LED system. So I'm going to talk a little bit about that later. Is maybe the future of LEDs is to do more than lumens. So the LED efficiency keeps going up. It reached the nitride LED efficiency is still increasing. Cree published this year in March that they were able to fabricate in their labs LEDs producing more than 300 lumens per watt. Just to keep in mind, today in commercial products it's more around 100 lumens per watt. But so LEDs are much more efficient than all the previous technologies, but the price is still high. So this is something where people have to work on, is to lower this price, because even if it's more efficient, if you want to penetrate the market, you are going to have to do something to make it cost less, so that people buy more. So we want, actually, if we want to reduce the price, we want more lumen per euro. And so a way to present that is that lumen per euro is lumen per watt times watt per millimeter square times millimeter square per euro. So the lumen per watt is mostly linked to the material, the internal quantum efficiency of the material. So we can see it's mostly a question of growth. The watt per millimeter square, it's also linked to the technology. So how we're going to process the LEDs. And the millimeter square per euro is linked to the manufacturing. It's a rough way of saying things, but all those things have to be taken into account and have to be optimized in order to reduce the cost. And so now, how nanophotonics can help? I tried to look into that, and I took this example with nanowires. This is something that was shown by people of Osram at a conference this summer. They are trying to, well, they want to use nanowires in order to be able to operate their LED at the maximum of the efficiency curve. If you look at the efficiency towards the current, there is a maximum around 10 amps per centimeter square. And today, because we want to get more light, we are operating here. So if we reduce the current, we're going to operate at the maximum, but we will get less light. So if we want to have the same amount of light per millimeter square operating at a lower current density, it's a good idea to use nanowires, because on nanowires you're going to have a greater developed area on your substrate compared to what it would be in the case of a 2D LED. So also you're going to be able to have, you're supposed to be able to grow good quality material, so you'll get more lumen per watt. If you have a larger area on each millimeter square chip, you'll get more watt per lumen. And you're going to also, if you manage to do that on silicon 8-inch wafers, it will really help your manufacturing cost. And so you're also supposed to get more millimeter square per euro, so you increase the total cost. So this is Eligia, which is a startup company that is working with those nanowires LEDs. They are able to grow, as I'm going to say more about that later, on silicon. So I talk about LED efficiency, so we can get more lumens. And something else we can do, and nanophotonics can help, in which nanophotonics can help, is to get more than lumens. Just a quick example. Well, here, nanophotonics, this is an example also of nanophosphor that are needed in some cases, especially with, if you want to convert light with nanowires. And actually, those nanophosphor, this is quantum dots. They can also offer a better color rendering, and they can also increase the efficiency, because you can better match the human eye response using those nanophosphor. And this is something else where nanophosphors are needed. This is an example of a monolithic LED array that this is a technology we're developing at Leti, currently at Leti. So we're able to process efficient micro LEDs with a pitch less than 10 microns. But for the moment, we get blue LED arrays. And if you want to convert light on those things and to get color, a color array, we're going to have to convert the light on a thin layer. A typical commercial phosphors, you need almost 1 millimeter phosphor thick layer of phosphor. So the solution could be, we're looking into that, to use quantum dots instead of standard YAG phosphors. Also, some other people are, those matrix, those array are also looked into by other people. This is people from Osram also. And again, yeah, there is this display that was shown in San Diego, and it was the first commercial laptop that was integrated quantum dot technology in the screen to get a better color running. So just to say, we want more lumen per millimeter square on this side here, and more lumen per watt, and also the thing that LED engine are going to is to get more than lumens. So this is the outline of my work of my talk. So more lumen per. So just to come back on those this efficiency issue. This is what we have in LED, typical LED. We have the emitting chip, and we have something that has to convert light, and this is everything is put into a package. So the main losses are due to conversion and this group of efficiency when operating at high current density. Well, I'm not going to come back here to the origin of the groups. There it's people don't really agree, but the thing is that for any LED chip that is measured today by everybody, there is a peak at 10 amps per centimeter square. And people now, because they want more light, everybody is operating their LED system around 35 amp per centimeter square. So as I said before, it would be nice to be able to come here, but we're going to get less light, which is something we don't want to. So just to come back to the loss, so as I said before, the losses due to conversion are 80%, and this is all the losses due to the drop of the efficiency. And if we reduce the current density, we could gain 26% more efficiency. This is what is happening at 35 amps per centimeter square. This is those losses we get between this low current density and this high current density. So this is well, actually, this is the approach of Ostrom I have to mention, and this is also why I choose to show you this to show you that big companies like Ostrom are working on nano wires for those reasons. Other thing concerning the conversion losses, the only way to fight against that is to match better the spectrum with the phosphor we use to convert the blue light. And we see that if the spectrum is better matched with the human eye response, we can just by spectrum engineering really increase the number of lumen per watt we get. I'll come back to. And there is a theoretical limit of 410 lumen per watt that we can get. And the same here. Well, just to say that the other losses we could gain are very small compared to the other to the increase of the spectral efficiency and the reduce of the current efficiency. We could. Now, with just working on the package, we think that we could only improve, well, people think that they could only improve by 5% their efficiency. And, well, also working on the phosphor. But so they came to this solution. So there is a group in Ostrom also trying to develop those core shell LEDs around nanowires. As I said before, it's to operate here. And this is not the and also, well, this is not the only one. They also managed to, they're also working on the nanophosphor they put around. They're not using quantum dots, but they are using some other kind of small size phosphors. And by engineering their phosphor, they can also, well, they're trying to improve their efficiency. And they fabricated here a white micro LED using nanowires. But this is not the only one. LEDA is also trying to address this cost issue using the same approach with core shell nanowires. So for the same reason, they are trying to reduce the current density they use. But they are also going to smart LEDs because they are able to grow their nanowires LEDs on 2mm silicon wafers. And this is very nice because this is a CMOS compatible technology. And what they are looking into is to, well, they can package their thing using, they are moving to wafer level integration and 3D integration, because by working on silicon, they can thin their silicon substrate, do some TSV, and contact their LED system from the backside and directly report that on a CMOS, on a functionalized other silicon substrate here. So this opens the way to many things. Oops, it's not shown here. Like the well, some smart lighting functions can be integrated because of the possibility of reporting that directly on the CMOS layer. Oops, I think no. Yeah, just to about the efficiency, there is something where Nanophotonics already help or can help, is the the light extraction efficiency. Well, current packages allow more than 80% of light extraction, and we could, the people from UCSB here compared the different approaches. You can use your shape your chip to extract light. That can work pretty well. This is some approaches used by Lumiled Cree and also Thora. This is a chip of Thora that grow directly GaN on GaN. And using those geometry, their chip geometry by geometric optics optimize their extraction. But when you don't want to, when you can't or you don't want to go to this chip scaling, many people use pattern Sapphire substrate. The thing is, it increase. Well, it's nice because it's very easy, and this is the cheapest way to produce LED wafers. But it's going to increase the defect density into the GaN layer, and it gives poor thermal conductivity. And then there are all kind of roughening of the gallium nitride after having removed the substrate in TFFC, thin film, in flipped chip technologies. And here is also an approach with Nanophotonics using photonics crystal. The thing here, it's difficult to fabricate, and you have to etch your gallium nitride layer to do that. Well, so if we want to go that, the extraction challenges are to adapt the patterning to the dip of the chip structure. You have different solutions. And if we want now to go further in the UV, we are going to have to increase more that extraction efficiency. It means that the light will have to get out of the structure faster. So what I think personally is that there is another approach that is coming recently that was proposed by a Rensselaer Institute, is to use an add-on layer instead of patterning your material or using the growth on the pattern substrate. because it avoids the etching of gallium nitride. I'm going to talk about more than lumens. Here is what I was saying before. Those people from Iridia, they really have an opportunity if they make their technology work to do more than just bringing light. They can connect. They have this that reduce the cost, but in addition, they can connect their LEDs in series so that they can have modules operating at higher voltage, which is a good way to simplify the driving of the LEDs. They can embedded intelligence into their device, and also they are going to a projection market, because using their approach directly on silicon, they could directly connect pixels. Glow also, I have to mention Glow, which is another company working with nanowires. They're also moving to displays, and as Iridia, actually, the use of nanowires should allows to go towards green and red LEDs using gallium nitride, because of the incorporation of the indium that is different on N planes and semipolar planes in the chip. So the idea here is using those nanowires to get true white LED without using phosphor conversion. This could be also an interesting way for those nanowire LEDs. And just to go back to those conversion problems, if we, as long as we are not able to produce white LEDs directly from GaN, we are going to use, we will have to use phosphors. And the thing, this is where quantum dots could be very useful, because as I said before, it would be nice to perfectly match the human eye response. And with quantum dots, just by using the size of the dots, if we talk about canard selenide quantum dots, we're able to change and to adjust the emission of the energy emission of the quantum dots. And this could be very useful in order to really adapt the spectrum to the human eye response. And it's also already used also to have a better color gamut in LCDs, color filters. It can also help for color saturation enhancement in some display. And this is what I was saying before. The benefit is to better match the human eye. This is with conventional phosphors using a yellow and a red phosphor. This energy is lost, and by using those red quantum dots, we can better engineer this spectrum. There are some drawbacks, which are the thermal stability and the thermal quenching of those objects right now. So there are many ways of to increase their efficiencies, but they could be very useful for LED application, and they are already used. They are getting used for displays. And as I said before, there are some, we are getting into that, the monolithic LED array to fabricate micro displays, but we are, for any kind of projection system, it's technology we just developed using a thin film flip chip technology. We were able to have those very small size LEDs. It's less than 10 microns, and we get very very nice properties of those micro-LEDs. This is the IV curve and the LV curve. So the process we have doesn't alter the properties of the material. And this also this flow is compatible to parallel or series interconnection, so we could make high voltage LEDs. And using that, we are also thinking about smart architectures with LEDs able to switch from parallel to series depending on the voltage. And we could also work on the dimming problem with LEDs. But as I said before, we are going to need if we want to improve after the flip chip the light extraction efficiency, we are going to have to look into nanostructuring of the surface, and for the conversion we'll need a thinner amount of material if we want to convert those by phosphor, the light by phosphor. That would take us to nanophotonics. And also on the wafer level packaging, there is in the LED trend there is this wafer level packaging approach. This is why people working on silicon as Aledia with their nanowires are going to wafer level packaging. It's because it's supposed to cut the costs drastically, and this is the common approach here. People are using this wafer into which they put their LED dyes. Then it's filled by phosphor, and they put an optic on that. So if we want to go further in the wafer level packaging, this is what we're trying to develop here, is to report directly our LED array on functionalized report substrate here. The substrate is removed, and then a functionalized substrate is used to convert light and for light extraction. So here, as I said before, if we want a color array, we'll have to have those different color phosphors, and this we can go to surface-mounted device and chip scale packaging, and nano patterning and phosphor needed for small pitch LED arrays will have to be developed. So I've tried to show that nanophotonics allows alternative substrate technologies. I talked about the extraction solutions, and also the importance of the conversion with novel color conversion particles. And in association with other components or other techniques or technologies, it could help us to go towards smart light solutions. And I think that's it. Thank you for your attention. I didn't write it. Okay.